All right, in this video, we are just going to look at a couple quick results about ways to combine continuous functions and arrive at a new function which is also continuous. So our first result tells us that the composition of continuous functions is continuous. Notably, if f is a continuous function from some domain A in the metric space M to N, and g is a continuous function from the metric space N to P, and if f of A lands in N, then the new function you get by doing g of f, which starts in A, goes to N, and then finishes in P, this is a continuous function in its own right. As I said, this just means the composition of continuous functions is continuous. All of this is really just to emphasize that the composition is even defined. So it's like if you want to do g of f, the range of f needs to be a subset of the domain of g. The statement is longer than the proof is going to be, because I'm going to use the sequential description of continuity. The sequential description gives you very fast proofs like this. So suppose that xn converges to x naught in A, which is the domain of f, but it's also the domain of the new function g of f that we'd like to evaluate. We automatically know that if this happens, then f of xn converges to f of x naught because f is continuous. I don't need to prove this convergence happens. We know it happens because f is continuous, and this is the sequential characterization of continuity. Now, this is a sequence of inputs converging in the domain for g. G is also continuous, so automatically I know what happens when I evaluate g on this sequence. Sorry, this marker is just about done. And that's it, because this is g of f of xn converging to g of f of x naught. Maybe I'll write that. Okay, so we've proved that the composition of continuous functions is also continuous. This is the only other set of results I want to look at in this video. So here we are assuming this time that f and g are continuous functions from the same domain to the same codomain. And we have these ways to combine them to produce a new continuous function if these combinations even make sense. So here you have to be able to take your outputs, scale them, and add them together. So this really seems like a result about working in Euclidean space. Here we have to have multiplication. So maybe one of these is a scalar, the other one might be a vector. Here I'm taking the reciprocal. So this really seems like a statement about real numbers. Okay, so just want to point out that this is really looking more at continuity of functions on, say, at least vector spaces, if not functions of a real number. These proofs are going to be very fast and short as well. Let me do the first two, and then I'll have you think about something for the third one. If xn converges to x naught in A, where again, I'm going to use the sequential description of continuity, then f of xn converges to f of x naught, and likewise, g of xn converges to g of x naught. That's just the sequential characterization of continuity. Now, I don't want to take a detour into proving the algebraic limit theorems. I assume that you've seen those and I can refer to them. So basically, I can take this convergence and scale it by number, same here, and then the limit of a sum is the sum of the limits. Okay, so I'm just going to write it down. Therefore, AF plus BG, this new function, which is a linear combination of f and g of xn, is equal to taking the sequence f of xn, scaling it by a, adding to that b times g of xn. Again, this is called like an algebraic limit theorem construction. This is going to converge to the linear combination of the limits. So the limit of the linear combination is the linear combination of the limits. So this is going to be a of f of x naught plus b of g of x naught. Okay, so let's do the next one in the same way. Again, if f of xn converges to x naught, same as the above, thus fg of xn, this new function that we are creating, well, it's defined as the product of f of xn and g of xn, and that converges to f of x naught, g of x naught, which maybe I'll write it back in this kind of new function notation. That is fg of x naught. Okay. The third one is the same kind of idea, but here I have the action of division. I've made a note here that the only thing I'm going to require is that f at x naught is non-zero, so that I'm not dividing by 0 when I compute the actual limit. I claim that that's good enough to be able to compute this. In other words, if inputs are near x naught, this denominator will also not be 0. So by insisting that f is continuous and non-zero at x naught, I'm implying that f is non-zero near x naught. That's actually a nice result to think about. So I would like for you to pause and think through why that statement holds. And then I'll come back and justify that and quickly do this. I think in order to do that, I'll probably erase these statements here so that we have a little bit more room. Let me prove that if f of x naught is, say, a positive number, then near x naught in the domain, f is a positive function. So suppose f of x naught, again, this computation really just makes sense if f is sending us to real numbers. Okay. Then since f is continuous, there exists a delta greater than 0, so that I'll say if x is in the delta neighborhood around x naught, but also the domain, then the distance from f of x to f of x naught, you might be expecting me to write less than epsilon over here, but I haven't even referenced an epsilon yet. That's hard to say. Instead, I'm going to put a specific measurement over here, which is f of x naught divided by 2. I'm not trying to prove f is continuous. I know it's continuous. So this is a valid choice of an epsilon to work with because this is a positive number, so divided by 2, it's positive. So I'm saying for this choice of like an epsilon measurement, I can find a delta so that if an input is within distance delta of x naught, then its output is within distance f of x naught divided by 2 of f of x naught. I.e., let me unfold this inequality. So I'll write negative f of x naught over 2 less than this without the absolute values, and then less than f of x naught over 2. Okay, this marker is done. Let's add f of x naught to every term in this triple inequality. So I'm going to get rid of this. When I add it over here, that's going to be negative f of x naught over 2 plus 2f of x naught over 2 all the way to get to f of x naught over 2, which is positive. That's really what I'm trying to say, is that it's greater than 0, strictly greater than 0. In fact, it's greater than this positive lower bound. And then over here, I would have a 3. Okay, so if you know that a continuous function is positive at some input, then it's positive near that input. And this is how you can prove that. That was really the heart of what I wanted to do with this third item. So kind of similar to what we did with 1 and 2. Then we'll just rely on sequences and algebra with sequences to say that if xn converges to x naught in A, f of xn converges to f of x naught. And then there's like a reciprocal expression with algebraic limit theorem, since this is really a sequence of real numbers now. So we would have 1 over f of xn converging to 1 over f of x naught. All right, so that wraps up this look at ways to combine continuous functions. All of them are probably what you would expect if you've been doing calculus for years now. So composition of continuous functions is continuous. And then we have these algebraic ways to combine continuous functions. Thank you for your attention.